So we are starting our last section of material for General Chemistry 1402. It's so sad. They're growing up so fast. Right? Okay, so we're talking about thermodynamics, and maybe you've heard of Newton's laws, and they kind of describe, baseballs flying through baseball diamonds and things. But this is more like the same idea, but all to do with getting things done. Motion, with whether it's a chemical engine inside your gut, or the chemical engine inside a leaf, or the chemical engine inside your car. It governs pretty much the world around you. And what's nice about it is that it's kind of similar to Newton's laws, where there's a set of laws that kind of govern the world around you. And it says kind of what's possible, what's impossible with regarding energy. For example, is there a lot of heat in the ocean? Right? 'Cause if you suck the heat out, what would you get? Ice, right? So there must be a lot of heat in the ocean. Well, is heat energy? Yes. Most definitely. So we're going to devise this ship, right, that moves along by sucking the energy out of the ocean and kicks out what in the back? Ice, right? Sounds pretty awesome. It would solve the greenhouse effect, right? It'd solve a lot of problems. But so much about thermodynamics is really just what's natural. Does that sound natural? Is water going to naturally, spontaneously just turn into ice and give off all this heat? Or is it the other way around, what happens naturally? What does ice want to do? Ice wants to, at room temp, sitting out there in the ocean, ice wants to melt. So it's a completely unnatural idea for us to suck heat out of the ocean and kick ice cubes out the back. It's unnatural. So that means it's going to take a lot of work, a lot of energy to do that. Well, that defeats the purpose of what we're trying to accomplish. So those types of ideas, they've kind of brought down to laws, and that's kind of what we're going to be talking about. The first of these laws is the First Law of Thermodynamics. Simply stated as you can never get something for nothing, or the work output can never be greater than the work input. So took this picture over at, if you've never been to Washington, D.C., and you like free stuff, man, hit the Smithsonian museums. They are so awesome. And they're all free. And they have a perpetual motion machine. Some guy put a lot of energy and work into this, getting everything nice and balanced and things. And once you get it spinning, man, it just keeps going on forever and ever and ever. It's at the Smithsonian Museum. But look at the statement of the First Law of Thermodynamics. You can never get something for nothing. Work output can never be greater than the work input. So question, Tegan, according to the first law, perpetual motion machines are impossible. But it's at the Smithsonian. Well, you look really closely. I don't know if you can see it, but that's an electric plug. It's plugged into the wall. It's just for show, right? So you think they would make a bigger stink out of the plug, but they really don't. So that's kind of. But anyway, it's kind of fun. The first law is written in equation form. Delta U equals Q plus W. Do you recognize any of these variables, Teresa? Delta U, Q, or W? Yeah, okay, the delta. What does the delta mean? You're right. When you put an arrow for a reaction, you put delta. That means heat. But when you put delta in front of a variable, it doesn't mean heat anymore. It means change. What minus what? Final minus initial. Or change. You're right. Since you're talking about the hardest one at the beginning, that's fine. Change in U. What's U? It's energy. It's energy. But they're not just going to blank energy. They're not just going to call it energy, because there's so many different forms of energy. I mean, you take a bottle of water, right? These little molecules are moving around. Well, that's one form of energy. They're rotating. That's a form of energy. They're vibrating. That's a form of energy. They're sticking together with one another. That's a form of energy. There's all these different forms of energy, and they're kind of all internal. So all the forms of energy, they call it internal energy. So that's what U is, the internal energy. And how they said that the energy of the universe is constant. They're talking about the internal energy, right? That all forms of energy, you can't create or destroy energy. So the change in internal energy is Q plus W. Q or W? Anybody recognize those? Heat is one of them. Which one is heat? Q. There's heat. One more, W, work. Okay. So if you think about the universe in general, the change in the internal energy of the universe, constant. All that's going on are things are being interconverted. Work to heat, heat to work. Things are just bouncing around. And what would be the units of all this stuff? We know the units of heat. Kilojoules, the most common one. We call it kilojoules. So if delta U is Q plus W, if Q is in units of kilojoules, what would work have to be in units of? You have to be able to add them together, though. So it would also have to be in units of kilojoules. Otherwise, you can't add them. Right? So they just got to be in the same units of energy. And kilojoules isn't the only unit of energy. I mean, you have joules. The Brits like the same thing on the Snickers bar. Calories or kilocalories, unit of energy. Okay. So that means delta U is most, but the most common is kilojoules. Okay, here's a, let's see if you've probably never had, maybe you had physics, right? You haven't had physics? Okay, Daisy, I'm pushing on this wall. Ah, so hard, right? Old man pushing on the wall. I'd say in 2 minutes I'm gonna start sweating here, right? Am I doing any work?
No.
My arm says I am, my body says I am.
You didn't move any distance.
But I didn't move any distance. Someone took physics. The brain says, no, I'm not doing any work because I'm not moving anything. The physicists, they say, the true scientists, they call themselves, right? Force times distance is work. If you're not moving anything, if nothing moved, you didn't do any work. All I'm doing is just generating what? The H word, heat. Right? I'm not doing any useful work. I'm not moving anything. Okay? So work really is just transformation of one form of energy to another is when you really get down to it. But that's probably more information than you need. The second law. The second law is based on human experience. Okay. So I purposely picked some of these things to see if we can make some generalizations. Rocks fall. Hot frying pans cool down when you take them off a hot stove. Iron rusts. A tire is punctured and the high pressure air shoots out to its lower pressure surroundings. Ice melts in a warm room. What do all these things have in common? What could you say, Diana, that all these things have in common? They're all changing. They're all what types of changes? Just, well, they're, what's the word for? Spontaneous, right? Spontaneous, natural. You can't stop these things from happening. They're just natural, right? They're all, now we're not supposed to use the word natural though. These thermodynamicists, they like the word spontaneous, so that's the word that we should use. And energy is what? Kind of, but a little more descriptive though. Energy is what? Energy is released, transferred, it's shifted, it's more spread out than what it was before, right? It's less, or energy is less organized than it was before in all those cases. Dispersed is the best word that they want you to use. Dispersed. Okay. Your textbook describes the second law this way. Vivian, what answers would you pick here? For any, what process? For any blank process, the blank must always increase. They describe it in a much more complicated way. Any spontaneous process, the blank must, trust her, he's right. The entropy must always increase. So let's take a little closer look at this. Entropy. So Erica, does ice melt in a warm room? Yeah. So the next question is, will the cold water molecules, Monica, give energy, because ice melts in a warm room, right? So you have warm air molecules and cold water molecules. Will the cold water molecules give energy to the warm air molecules, or do the warm air molecules give energy to the cold water molecules? Yeah, this exactly the second one, right? Does that make sense? No, they can be moved. Stuff moves, but the point is energy is always going from high to low, right? That you can't stop energy being dispersed, and entropy is supposed to be a measure of that. Entropy, delta S, is a measure of how spread out the blank is in a system. Now, some of these answers there might be more than one answer, but there's one best answer. How spread out the what is in a system. Heat is correct, but there's a better answer, because the answer isn't always heat. Molecules is a good answer, but the answer isn't always molecules. Internal energy, because it covers all forms of energy. Okay. The third law of thermodynamics. A crystal with no imperfections at 0 Kelvin has an entropy of 0. What is 0 Kelvin? Negative 273 Celsius, that's right, yeah. It's the temperature that's okay, right? Theoretically, you can't get any absolute 0. Theoretically, you can't get any lower than it because there's no more heat to remove. Things just aren't moving enough for you to slow them down anymore. Free energy. Oh, but why? Why have this third law? You have this whole third law so we can do this. So we can put numbers in and calculate delta G. Delta G is going to be a big deal. Delta G is going to be a big deal. But we need to be able to put in numbers for this stuff. Now, delta H, that was, do you remember what that was? Heat, or the fancy word was, started with an E, enthalpy. So you measure the heat given off in a reaction. So you can measure delta H. But delta S, that's pretty hard to measure, the entropy. So there's going to be tables. We want tables to actually calculate delta S. And that's the whole reason for the third law. So that you can have a baseline to actually measure entropies from. So this equation for delta G, it's a huge deal, because you can be talking about some really complicated systems, like what's going on inside your body, drug-body interactions. Will this enzyme actually work? Right? Does it have the energy to do it? A lot of it comes down to this, because it has to be natural, it has to be spontaneous. Otherwise, it's not going to, these things aren't going to occur on a very complicated basis. So with one simple direct equation, you can make some pretty nifty predictions. So we mentioned that delta G is going to be huge, important, but we call delta H what again? Enthalpy. What were its units? Do you remember what very often they were? Kilojoules per mole. Yep. How about T? What is T, anybody? Temperature. T is temp. Yeah, it has to be in units of Kelvin. And then delta S we said was entropy. Okay. And where are we going to get these numbers? From tables. Now, one more is delta G. What's that one called? Well, there's going to be different delta S and different delta H's for compounds. It's free energy. There are going to be different numbers for different compounds. We have to calculate this stuff, and we'll work on that. But delta G was the free energy. I guess we're supposed to call it whose free energy? So there's the G. Gibbs. Yeah. Gibbs free energy. Okay. I think when you start calculating delta G, we'll talk about why it's such a big deal, but just I want to cover this trick so I don't forget first. You get this stuff from tables we mentioned. And I don't know why they do this, but delta S is in joules per Kelvin mole. So it has to be in Kelvin, so the Kelvins will cancel and you multiply it by temperature. But why do they have it in joules, right? Because then you got to convert to what? Kilojoules, otherwise you're going to get the wrong answers. So all the tables are like that. So just I want you to notice that right off the bat. Okay. This sentence here is huge. When which term is less than 0, the process will be spontaneous. It'll occur. You can't stop it. It'll be natural. Which one?
Entropy.
Not entropy. It's the delta G. That's why it's such a big deal. Everyone's interested in the Gibbs free energy. Is it negative? Is it negative? Is it negative? How negative is it? It's got to be a big negative number, and then it'll be spontaneous. If it's positive, well, then it would be not spontaneous, but non-spontaneous. If it's 0, then what?
No, it's nothing.
Or close to 0, it can go either way. It doesn't really matter. It's kind of like a baseball on a flat table. It's not going to roll either way. I mean, if the wind blows this way, it blows that way, whatever. It can go any way. How do we get numerical values for all these delta G, delta H, and delta S? We use what again? Tables. Okay. So a reaction. We're going to calculate delta G for some reaction. Calculate the Gibbs free energy for some reaction. It's more likely to be spontaneous if it is something. Change in entropy is something. Temperature is something. Circle your answers. Now remember, what's the trick? Delta G needs to be what to be spontaneous?
Negative.
Negative. Circle your answers so that delta G is as negative as possible. So Danny, how did you answer the first one? Exo or endo? Exo, great, because then, right, then delta H will be negative. That'd give a big negative delta G. The change in entropy, Gabby? Positive. Do you guys see why? Because you're subtracting it, right? So you want this to be positive. If delta S is negative, you have a negative times a negative is a positive, that's going to go the wrong way. Temperature. Alyssa, what did you do for temperature? High or low temp? High. Very good. Because then you're subtracting this big negative number, right? Can temperature ever be less than 0 in this equation?
Yes. No.
It can't be because it's in Kelvin. Yeah. Okay. Simply by looking at a reaction, What do you think, Sabina? Can you tell if the change in entropy will be positive or negative? Man, that's a tough question. Simply by looking at a reaction. How can you tell? There is a way. Because which state has a really high level of dispersal? Solid, liquid, or gas? Gas, right? So if you have a reaction that's producing a whole lot of gas, well, that's going to, right, final minus initial, and it's producing a whole lot of gas, producing a whole lot of dispersal, that's going to have a high positive delta S. If you have a lot of what molecules on the reactant side, there'll be a big negative delta S. A lot of what type of molecules? Gas, right? Because now the gas, you have a whole lot of dispersal at the beginning. It's all disappearing. So in this question, this very first question, before we answer it, right, because they want us to calculate it. Let's just jump to this first part. Does the entropy of the chemical system increase or decrease? Delta S is going to be, now we're not going to calculate it yet. Delta S is going to be what for this reaction? Positive or negative? Why negative? Why negative? How many gas molecules are on the product side? There's more than one. On the product side, there's 2, right? Because this is a liquid. So there's 2 gas molecules on the product side. How many are on the reactant side? 4. So we started out with a whole lot of entropy. But then things got slammed down into less dispersal. So delta S should be negative. It should be less than 0. Okay, so we go ahead and we calculate it. Now, you'll remember how to do this if you remember how to do it for delta H. We had the exact same thing, but they said delta H 0. What did the little 0 mean? It meant you could use the tables. It meant standard conditions. And how did we get it? Do you remember? We used tables. I mean, I'm going to erase delta H. We're not going to do delta H, but how do we do it? We use tables. If I set this up, will you remember? Was it reactants minus products or products minus reactants? It's always final minus initial, so it must be products minus reactants. So we're not doing delta H. We have to find a delta S table. So get rid of that H and make an S. Okay. And I doubt if anybody brought their book, so I have to give mine to somebody here. Okay. And people sit in the back, they think they can get out away from stuff, right? Right, Erica? That's how things go.
No.
Okay, so what we need to do is we need to find the delta S. Now what I did is I opened it up to the very back. Like what page is that on?
A8, A9.
A8.
A8.
A8. And
A9.
okay, so way in the back, right? Appendix A. So she has to find, now we do products minus reactants. We have 2 carbon dioxide molecules. We need to know what the delta S is for carbon dioxide, and it needs to have a G on it. Right? So it should be with the carbon stuff. And it should be CO2 gas. And then go to the S table. 213.7. Right? Let's just make sure we don't have to erase everything. I bet you got it, but I just want to make sure. Yeah, so the S table, and it's CO2. Yeah, you're exactly right. Okay, so keep going there, Erica. So we have 2 times 213.7. Now we need H2O liquid, not the gas one. It has to be the liquid. 69.95. Okay, so those are our products minus the reactants. So we need C2H4. And it has to be a gas.
Yeah.
Okay.
Or is 219.2.
Okay. And now we have to take 3 times oxygen gas. 205. Okay. So thank you, Erica. So go ahead and calculate it now. Products minus reactants. Hopefully we'll get a big negative number. Thank you very much. Negative 267. Really? God, everyone's getting two. We have two negative 267s. Okay. All right. Yeah, that's what people are getting. You should be getting that. Now, you didn't get points docked if you don't write the what? The units. Now, do you know what the units are? Or where do you look to get it? Just look in the table, right? What are the units? What are the units? Go ahead and read out the units for us. For the S in the table. J over K mole. Okay? So just get it from the table. We're good? For each of the following reactions, state whether the reaction is spontaneous or non-spontaneous or is easily reversible. That is, a mixture with significant amounts of reactants and products at equilibrium. What's the trick to doing this? Jasmine, how do you figure this stuff out? Okay. What's that? Oh, counting gas molecules to predict whether delta S is positive or negative. This is to state whether the reaction is spontaneous or not. What symbol was that? Yeah, that's that delta G thing. Whether it's spontaneous or non-spontaneous. So that was all with, and that's probably why they just gave us this one. Thank goodness, otherwise you have to calculate it. But they all look like, they're all positive, so you would say they're all non-spontaneous. Now I'd agree, except this last one, the book is probably going to say what? They're going to say reversible. Why? Because it's very close to what number? 0. Very close to 0. So a small negative number, you'd say reversible too.
So like negative 2.6?
Yeah. Anything really close to 0.
So on a test or quiz, if it tell like when it comes out in 2.6, would it be reversible?
Mm-hmm. Calculate the standard enthalpy change and the standard Gibbs free energy change for the following reactions using thermodynamic data. Interpret the signs. So, So before we list out all the data that you need, what does this part mean? Okay, to say what's going to be spontaneous or not, that's for the delta G part. What about for the delta H part? What are the two words? What are the two words for that? Like if delta H is negative, you say exothermic. If delta H is positive, you say endothermic. Okay, so we need the data. Let's see, so we handed out the book. Let's make a little table here. Delta H, we'll put on top. And then let's just do delta H first, and someone else can do all the delta G's. So how about the delta H for COCl2? It has to be gas. Negative 220.1. And H2O liquid, the delta H. Should be with hydrogen. You find it? Should be with the hydrogen. Yeah, there's H2O liquid though. It has to be that one. And right? Oh, that's H2O too. So you read it. I'm old. Okay. What'd you say? Negative 2? Negative 285.8. Now CO2 gas. Okay. And then HCl gas. Okay, and let's hand it over to Gabby there. Now, Gabby, now give us all the delta G0 numbers, starting with the COCl2 gas. And make sure you look on the delta G table column. COCl2 gas. Negative 206, I'll call it. Okay, H2O liquid. Negative 237. Okay. CO2 gas, delta G. Negative 394. And then HCl gas. Negative 95. Okay. Now give us the units for the delta H. What does it say in that table? Kilojoules per mole. And what does it say are the units for delta G? Kilojoules per mole. Awesome. They're consistent. Okay, now you have everything you need. Thank you very much. So just calculate your delta H and your delta G. Right? Products minus reactants. Negative 712 for delta H. I got negative 712 for delta H. Anybody else get that? No?
Yeah, I got 72. Yeah, I got negative.
Negative 72 for delta H. Did anybody else get that? Oh, you got it, Erica? Vivian got it? Okay. How about the delta G? Negative 141? Anybody else get negative 141? Excellent. Okay. So you should be getting those. Same thing. Alrighty, isn't that nice? Nice Friday, there's nothing left. I should have given you more problems in here.